48 years ago, the universe whispered. A 72-second radio signal sliced through the cosmic silence from the direction of Sagittarius, then fell quiet. Today, from the same patch of sky's dark depths, something else is racing toward us, 3I Atlas. This interstellar visitor's chemical fingerprint defies easy explanation, and its timing stretches the word coincidence to the edge of belief. It's as if the universe were laying a breadcrumb trail, a mysterious radio transmission, and a far-travelled messenger, sharing more than a celestial return address stamped from Sagittarius. What we must determine is whether humanity has stumbled into the greatest coincidence in the history of astronomy, or whether, for the first time, we've truly brushed against intelligence beyond Earth. Part 1. The Coincidence. 2 mysteries, 1 constellation, 48 years apart. In 1977, a radio telescope in Ohio captured something that shouldn't exist. A signal so powerful and so precisely engineered that astronomer Jerry Amon scrawled "Wow" in red ink across the printout. The signal came from Sagittarius, aimed toward the crowded core of our galaxy. It lasted exactly 72 seconds, then vanished forever. Now in 2025, another visitor has arrived from that same region of sky. This time it isn't an invisible radio wave dancing across a screen, but something tangible, something real, a mysterious object hurtling through space on a trajectory that all but shouts, "I don't belong here." They call it 3 Atlas, 3I Atlas, the third confirmed interstellar visitor to enter our solar system. And like that radio whisper decades ago, it's approaching us from Sagittarius. Is this coincidence merely a coincidence? In a universe with 200 billion galaxies, each home to tens of billions of stars, what are the odds that 2 of the most perplexing astronomical anomalies would light up the same patch of sky? Sagittarius is more than decorative ink on our night. When we gaze at those familiar star patterns, we are in fact looking straight toward the Milky Way's gravitational maelstrom, home to Sagittarius A Spura, a supermassive black hole, 4.3 million times the mass of our Sun. It's the Times Square of astronomy, crowded, energetic, and never asleep. Radio waves flood this region like city noise, making it the most conspicuous and the most challenging place to hunt for cosmic signals. Because teasing a true transmission out of nature's static is brutally hard. The cosmic coincidence grows more intriguing when you consider the WOW signal's original frequency. At 1420 MHz, it sits squarely within what SETI researchers call the water hole, a relatively quiet stretch of the radio spectrum bracketed by emissions from hydrogen and hydroxyl. For decades, scientists have debated whether this frequency is the natural gathering place for interstellar communication. Think of it as a cosmic phone number, one any technologically advanced civilization would instinctively know to dial. The hydrogen line is especially meaningful. At 1420.4 MHz, hydrogen atoms undergo a quantum transition that any species capable of receiving radio would recognize. It's bedrock physics, a universal constant that transcends culture, biology, and technological history. If you wanted to send a message that could be understood across interstellar distances, this is the frequency you'd choose. And here, our story takes an unexpected turn. On July 1, 2025, 3I Atlas was discovered by the Atlas Survey System in Chile's Atacama Desert. Unlike the billions of rocks that keep quiet, closed orbits within our solar system, this object is on a hyperbolic trajectory, meaning it isn't gravitationally bound to our Sun at all. It comes from somewhere else entirely, crossing the gulf between stars until our gravity merely nudged its path and drew it briefly into the inner solar system. The numbers don't lie. Its orbital eccentricity exceeds 1, the mathematical fingerprint of an interstellar wanderer. It isn't a local asteroid that drifted too far, nor a comet jostled loose from the Oort cloud. 3I Atlas is a true visitor from beyond, carrying the chemistry and the secrets forged around an alien star. What makes this visitor especially exciting is our unprecedented opportunity to study it. When Oumuamua, our first confirmed interstellar visitor, swept through the solar system in 2017, it vanished into darkness almost before we could aim our telescopes. Comet 2I Borisov in 2019 gave us a slightly longer window, but it still left before truly comprehensive observations were possible. 3i Atlas is different. Its trajectory grants us months of detailed scrutiny, allowing us to bring the full toolkit of modern astronomy to bear. The James Webb Space Telescope has already begun capturing its infrared spectra, and Hubble is constraining its size and rotation. Ground-based observatories worldwide are tracking changes in its coma and tail as solar radiation awakens dormant volatiles in its nucleus. We are witnessing something historically unprecedented. We have the chance to dissect material from another star system, to analyze the chemical fingerprints of worlds we may never directly observe. But that isn't what makes this story truly extraordinary. 3i Atlas turns from mesmerizing to potentially revolutionary because of anomalies emerging in our observations. Preliminary spectral data reveal an unusually high carbon dioxide to water vapor ratio, with some measurements suggesting roughly 8 point most. Comets in our own solar system show the opposite preference. Then there are nickel emission lines that fail to match the ion signal, overturning our understanding of how these elements typically co-appear in a comet's atmosphere. The object's small size, Hubble measurements suggest a maximum diameter of only about 5.6 kilometers, and possibly smaller combined with its pronounced activity, has led some astronomers to call it an overperforming comet. It is producing more dust and gas than objects of similar size usually manage, as if it were playing by an entirely different set of rules. Before we dive into speculation, we have to acknowledge a simple rule. Extraordinary claims require extraordinary standards of evidence. The history of astronomy is packed with anomalies that looked alien, until better data revealed entirely natural explanations. Pulsars were once suspected as potential extraterrestrial signals. Fast radio bursts inspired similar whispers until we understood their cosmic origins. But what if this time is different? What if two inexplicable phenomena arising from the same patch of sky mean they're more than statistical noise? What if we received a signal 48 years ago and now we're witnessing its follow-up? This documentary will explore those questions without losing scientific rigor. We'll examine the data with clear eyes, separate measurement from conjecture, and let evidence not expectation steer our conclusions. We will retrace the histories of these twin mysteries, review the latest scientific analyses, and consider possibilities ranging from the everyday to the transformative. The WOW signal and 3i Atlas may ultimately prove unrelated, two riddles born of humanity's tendency to find patterns in randomness. Yet their convergence offers something equally valuable, a lens through which to see how little we truly know about the cosmic neighborhood we call home, a place that keeps surprising and humbling us. As 3i Atlas continues its journey through the solar system, drawing near Mars in early October, looping around the Sun, and beginning its long return to interstellar space, we have a singular opportunity to listen, to watch, and to reflect. Because in this universe, if two mysteries from the same patch of sky can find their way to our cosmic doorstep, then anything is possible. Part 2. The Night of the WOW Signal. August 15, 1977. While most Americans slept, a radio telescope in Ohio kept its nocturnal vigil, slowly sweeping the heavens for whispers of intelligence between the stars. The Big Ear telescope was unassuming, essentially a vast metal trough carved into rural Ohio, its length comparable to 3 football fields. Unlike the dish antennas we usually imagine, Big Ear used a fixed reflector design, relying on Earth's rotation to rake the sky. That meant astronomers couldn't rapidly repoint to targets of interest. Each patch of sky drifted through the beam for only 72 seconds, and then it was a 24-hour wait for a second look. On this particular night, as the constellation Sagittarius slid into the telescope's field of view, something extraordinary happened. The receiver logged a signal unlike anything in its archives, a narrow-band transmission pinned at 1424.55 MHz, its strength rising steadily and then fading away, exactly as expected for a celestial source crossing a drift scan beam. But it was the signal's power that set it apart, astonishingly strong. Fresh reanalyses suggest a peak intensity near 250 Janskas, roughly 30 times the typical background. In the world of radio astronomy, that isn't a murmur, it's a shout. A few days later, volunteer astronomer Jerry Amon paused over an impossible-looking sequence while reviewing that night's computer printouts. 6EQJ5. The characters rose and fell in perfectly symmetric fashion, matching exactly the expected profile of a point source drifting through the telescope's beam. Eamon grabbed a red pen, circled the anomaly, and wrote a single word in the margin. Wow! The signal's traits read like a textbook example of the kind SETI researchers had theorized for extraterrestrial transmissions. It was narrow-band, implying an artificial origin. Nature rarely produces such razor-precise frequencies. It appeared to come from a fixed point in space, not from a moving satellite. And most tantalizing of all, it landed almost exactly on the hydrogen line, a frequency many scientists consider ideal for interstellar communication. Big Ear's unusual design employed two side-by-side feed horns, allowing it to observe two adjacent sky strips simultaneously. As the celestial source drifted through the field of view, it should have lit up both beams in sequence, about 3 minutes apart. Yet the WOW signal appeared in only one beam, injecting uncertainty into its exact location and complicating follow-up searches for decades. The Ohio State University team immediately grasped the signal's significance. Within days, they repointed other telescopes toward the suspected region and mounted an intensive search. They found nothing. The signal vanished as mysteriously as it had arrived, leaving only a printed record and a growing conviction that they had witnessed something without precedent. This marked the beginning of one of the most extensive follow-up campaigns in SETI's history. Over the next several years, dozens of radio telescopes around the world aimed at the suspected coordinates of the WOW signal. The Very Large Array VLA, the Arecibo Observatory, the Parkes Observatory, and countless others joined the search. Some telescopes monitored continuously, others observed intermittently. All efforts came up empty. The signal's failure to repeat posed a fundamental challenge for SETI researchers. How do you verify a transmission that occurred only once and never returned? How do you distinguish a genuine extraterrestrial beacon from an unknown natural phenomenon or an unrecognized source of interference? The WOW signal became a textbook case of what philosophers call the problem of induction, drawing general conclusions from a single specific observation. As the years passed, a cascade of explanations tried to account for its peculiar traits. Some argued it might represent a previously unknown kind of celestial object, perhaps a neutron star undergoing a rare magnetic reconfiguration, or a hydrogen cloud illuminated by some distant energetic event. Others ventured more exotic ideas, invoking collapsing stars, black holes, or labyrinthine interstellar phenomena triggered by cosmic collisions. One especially controversial explanation surfaced in 2012, when Antonio Paris suggested the signal could have come from a comet carrying a surrounding hydrogen cloud. In theory, sunlight could excite hydrogen to emit at the hydrogen line frequency. Paris identified two comets, 266P Christensen and 335P Gibbs, that might have been in the right place in 1977. Veterans of Big Ear noted that a comet's motion across the sky would have been obvious, whereas the WOW signal appeared fixed. The hydrogen cloud hypothesis also struggled to account for the signal's extraordinary strength and narrow bandwidth. More fundamentally, radio telescopes have not detected similar emissions from hundreds of other comets over the decades. The controversy highlighted a key principle in SETI: the burden of proof. For a signal to be considered genuinely extraterrestrial, it must not only lack a conventional explanation, it must also display compelling hallmarks of intelligence. The WOW signal meets the first criterion, but falls short on the second. Its anomalies are unmistakable, yet they could be explained by an as-yet unknown natural phenomenon. Recent reanalyses have offered a fresh perspective on the signal's properties. In 2024 and 2025, researchers used improved data processing techniques to extract more information from Big Ear's original archives. They narrowed the signal's possible location, confirmed its anomalous strength, and ruled out several classes of terrestrial interference. Most importantly, they identified features in the surrounding data consistent with a natural hydrogen maser explanation: hydrogen gas amplifying radio waves in response to a distant energetic event. This hydrogen maser hypothesis has gained broad support among SETI researchers. Hydrogen masers can arise naturally when interstellar gas is pumped by nearby energy sources, producing laser-like emission at radio frequencies. Hydrogen masers are exceedingly rare in interstellar space, but they have been observed in some star-forming regions and around certain types of evolved stars. Such a maser could be triggered by magnetar flares, supernova shock waves, or similar high-energy events, and in principle could produce a signal consistent with the WOW detection. Even so, this seemingly natural explanation carries profound implications. If the WOW signal was indeed a hydrogen maser event, it would represent an astrophysical phenomenon without precedent. Its razor-precise frequency, its textbook perfect time profile, and its appearance at the very wavelength long argued by SETI researchers to be the likeliest channel for interstellar communication, all of these push coincidence to its limits. The signal's legacy extends far beyond its particulars. It proved that Big Ear could detect powerful transmissions across interstellar distances. It validated SETI's search strategies and inspired a generation of radio astronomers to take the possibility of extraterrestrial intelligence seriously. Most importantly, it helped define what counts as credible evidence in SETI, standards that still shape how we evaluate anomalous signals today. As we'll see, those standards become especially relevant as we scrutinize our current interstellar visitor, 3I Atlas, and they fuel tantalizing speculation about a possible connection to the famous signal from 40 years ago. Part 3: The Hydrogen Line. The universe's signal. In the vast library of the electromagnetic spectrum, every frequency tells a different cosmic story. One in particular stands out, not only to human scientists, but to any intelligent civilization that has ever looked up and wondered whether it was alone. At 1424.0575 MHz, something remarkable happens to the hydrogen atom. The simplest and most abundant element in the universe undergoes what's called a spin-flip transition, an almost imperceptible event in which the atom's lone electron occasionally flips its magnetic orientation relative to the proton, releasing a tiny packet of energy in the form of radio waves. This transition would occur in any single hydrogen atom only once every roughly 11 million years. But across the vastness of interstellar space, where hydrogen clouds stretch for light years and contain unthinkable numbers of atoms, the resulting 21-centimeter emission becomes a steady signal we can constantly detect. It's the universe's background music, played on its most basic instrument, the building blocks of stars, planets, and life itself. What makes this frequency extraordinary is not just its ubiquity, but its inevitability. Any civilization that discovers radio astronomy will find the hydrogen line, measure its precise frequency, study its behavior, and recognize its importance. Unlike cultural artifacts or biological signatures, the hydrogen line is a universal constant, a cosmic landmark that transcends species, technology, and evolutionary path. Early SETI researchers understood this well and argued that the hydrogen line is nature's built-in interstellar hailing frequency. In 1959, Giuseppe Cocconi and Philip Morrison proposed in their landmark paper that a radio-capable civilization would discover and use the hydrogen line frequency for interstellar communication. Their logic was crisp. If you want to send a message any radio-using civilization can understand, you choose a frequency they will inevitably find and monitor. The hydrogen line sits within what SETI pioneers called the water hole, a relatively quiet region of the radio spectrum bracketed by neutral hydrogen emission at 1420 MHz and hydroxyl OH emission around 1660 below 170. Between these natural spectral beacons lies a band where cosmic radio noise is minimal, the zone Bernard Oliver dubbed the closest thing to a universal quiet channel. The symbolism wasn't lost. Hydrogen and hydroxyl H and OH combine to form water, life's most fundamental molecule. In a universe where countless civilizations might gather around their own watering holes to share information and sustain social ties, perhaps advanced species would naturally congregate at this cosmic water hole to carry on interstellar conversation. But the significance of the hydrogen line goes beyond symbolism. Its physical properties make it ideal for long-distance communication. At a 21-centimeter wavelength, It slips through interstellar dust and gas that would block shorter wavelengths. Its naturally narrow line enables efficient transmission with lower power. Most importantly, it helps avoid interference. Many nations maintain radio quiet protections near 1420 MHz specifically for astronomical research. When the WOW signal showed up at 1420.455 MHz within about 50 kHz of the hydrogen line frequency, it seemed to validate decades of SETI theory. This is exactly the kind of signal researchers predicted they might find: narrow band, powerful, and parked at the universe's most sensible hailing frequency. Yet that apparent confirmation carries its own complications. Because the hydrogen line also occurs in nature, it's a frequency where astrophysical phenomena can masquerade as artificial transmissions. Hydrogen masers, narrow band bursts produced when interstellar gas is pumped by nearby energy sources, can also appear in precisely the band that SETI scientists monitor most intensely. These hydrogen masers are rare in the cosmos, but they've been observed in star-forming regions and around certain types of evolved stars. They can be triggered when interstellar gas is energized by nearby sources. Even high-energy events such as supernova remnants, magnetar flares, or gamma-ray bursts can set them off. SETI researchers call this the natural camouflage problem. The very frequency where we expect to find intelligent signals is also one that nature can generate on its own. Therefore, scientists no longer rely solely on frequency matches to identify an artificial signal. They also look for complex modulation patterns, precise frequency drifts to compensate for relative motion between source and receiver, or structured information content, features that natural sources struggle to mimic. They seek repeatability as well, signals that reappear from the same location, hinting at a persistent transmitter rather than a one-off event. The waterhole concept has also evolved, with researchers proposing additional biologically relevant molecular transitions, such as the 23 GHz ammonia line, various organic compounds, and even quiet windows in the cosmic microwave background as alternative interstellar watering holes. Even so, the hydrogen line retains a special status in SETI. The ongoing Breakthrough Listen program dedicates major observing time near the hydrogen line frequency, and China's 500-meter aperture spherical telescope, FAST, regularly monitors this band for SETI targets. Even optical SETI searches sometimes employ laser wavelengths associated with hydrogen transitions that fall within the visible spectrum. The hydrogen line matters not only for detection but for transmission. If humanity ever decides to announce its presence to the galaxy, many proposed schemes use the hydrogen line as the carrier. Its universal recognizability makes it an ideal conduit for interstellar messaging, ensuring any recipient will immediately infer an artificial source. In recent years, advances in technology have dramatically boosted our sensitivity and resolution at the hydrogen line frequency. Modern radio telescopes can discriminate signals that differ by only a few hertz while surveying bandwidths of megahertz. They can measure polarization signatures that reveal distant magnetic field geometries, and crucially, they can process data in real time, enabling rapid follow-up on fleeting events instead of waiting days or weeks for offline analysis to uncover an anomaly. This technological revolution is especially relevant as we consider 3i Atlas's passage through the solar system. If this interstellar visitor is truly connected to the WOW signal, if both are pieces of a grand interstellar communication scheme, then the best time to search for repeat transmissions is as the comet passes major solar system bodies. The hydrogen line offers a perfect window for such a campaign, precisely defined, universally recognized, and carefully protected from interference. As 3i Atlas approaches Mars, swings past the Sun, and nears Earth, radio telescopes worldwide will have a chance to listen at the exact frequency where the WOW signal first appeared 40 years ago. Whether or not we hear anything, the search itself is profound, humanity continuing to test the possibility that we are not alone, willing to read messages written in the universe's most fundamental language. Part 4. The Unrepeatable Mystery. In science, reproducibility is everything. Discoveries that refuse to repeat are met with deep skepticism and often relegated to the footnotes of history until independent verification turns doubt into acceptance. The WOW signal has dwelt in that scientific purgatory for 48 years, too significant to dismiss, too solitary to fully embrace. Follow-up observations began almost as soon as Jerry Amon circled that famous printout in red. In the weeks after the discovery, radio telescopes around the world aimed at the suspected source region and launched an intensive search. They found nothing. The signal vanished as mysteriously as it had appeared, leaving only a printed record and a growing sense that they had witnessed something without precedent. This also marked the beginning of one of the most extensive follow-up investigations in SETI's history. Over the ensuing decades, radio telescopes around the world joined the search. The Very Large Array, the Arecibo Observatory, the Parkes Observatory, and countless others took part. Some facilities monitored continuously, others intermittently, but in the end, all efforts came up empty. The signal's failure to repeat posed a fundamental challenge for SETI researchers. How do you verify a transmission that occurred only once and never again? How do you distinguish a genuine extraterrestrial beacon from an unknown natural phenomenon or unrecognized interference? The WOW signal became a textbook example of what philosophers call the problem of induction, how to draw general conclusions from a single particular observation. As time passed, a range of explanations emerged to account for its peculiar features. Some proposed that the signal might represent a previously unknown kind of source, perhaps a neutron star undergoing a rare magnetic reconfiguration, or a hydrogen cloud illuminated by some distant energetic event. Others ventured more exotic ideas, invoking phenomena associated with black holes or collapsing stars, possibly triggered by interstellar collisions. Among the proposals, Antonio Paris's 2012 hydrogen cloud hypothesis drew significant controversy. He argued that the signal might have come from two comets, 266P Christensen and 335P Gibbs, that could have been in the source region in 1970. The SETI community responded quickly and largely skeptically. Veterans of the Big Ear telescope noted that a comet's motion across the sky would be obvious, whereas the WOW signal appeared stationary. The hydrogen cloud hypothesis also failed to account for the signal's extraordinary strength and narrow bandwidth. More fundamentally, radio telescopes have not detected similar emissions from hundreds of other comets over the decades. The debate exposed a core issue in SETI, the burden of proof. For a signal to be judged genuinely extraterrestrial, it must not only lack conventional explanations, it must also display compelling hallmarks of intelligence. Signal meets the first criterion, but is less convincing on the second. Its anomalies are plain to see, yet they could still be explained by natural as yet unknown phenomena. In recent years, reanalyses have offered a fresh perspective. In 2024 and 2025, researchers used improved data processing techniques to extract more information from Big Ear's original data. They narrowed the signal's possible origin, confirmed its anomalous strength, and ruled out several classes of terrestrial interference. Most importantly, they identified patterns in the surrounding data that may support a hydrogen maser explanation, hydrogen gas amplified by a distant energetic event. This hydrogen maser hypothesis has gained broad support among SETI researchers. Hydrogen masers are exceedingly rare in interstellar space, but they have been observed in star-forming regions and around some evolved stars. Hydrogen maser events are exceedingly rare, but they have been observed in certain star-forming regions and around evolved stars. When interstellar gas is energized by a nearby power source, a hydrogen maser can arise. Even high-energy phenomena such as supernova remnants, magnetar flares, or gamma-ray bursts can trigger maser activity. SETI researchers call this the natural camouflage problem. The very hydrogen line frequency where we hope to find intelligent signals is also one that nature can produce on its own. In effect, a hydrogen maser is a kind of natural radio laser, capable of generating intense narrowband emission that neatly mimics the artificial signals humans expect. Therefore, scientists no longer rely on frequency alignment alone to search for artificial transmissions. They also look for other hallmarks, complex modulation patterns, precise frequency drift to compensate for relative motion between source and receiver, or structured information content, features that natural sources struggle to reproduce. To guard against natural phenomena masquerading as technology, SETI researchers also demand repeatability, signals that recur from the same sky location, indicating a persistent transmitter rather than a one-off event. The hydrogen line concept has continued to broaden. Some researchers now propose enlarging the waterhole band to include other biologically relevant molecular transitions, such as the 23 GHz ammonia line, various organic compounds, and even quiet windows in the cosmic microwave background. Even so, the hydrogen line still holds a special place in SETI. As modern radio technology advances, especially with fast and other world-leading telescopes, Researchers can conduct hydrogen line observations with unprecedented sensitivity. These facilities let us monitor exquisitely faint signals with precision and process, and analyze them immediately. Even in optical SETI, it is sometimes possible to target laser wavelengths associated with hydrogen transitions. The hydrogen line's special status extends beyond detection to transmission. If humanity ever decides to announce our presence to the galaxy, many proposed beaming schemes involve the hydrogen line as the carrier. Its universal recognizability makes it an ideal frequency for interstellar messaging, ensuring any receiver will instantly infer an artificial rather than natural origin. In recent years, technological progress has dramatically increased our sensitivity and resolution at the hydrogen line frequency. Modern radio telescopes can distinguish signals that differ by only a few hertz while surveying megahertz of bandwidth. They can measure polarization signatures that reveal magnetic field geometries in distant sources, and most importantly, they can process data in real time, enabling rapid follow-up on fleeting events instead of waiting days or weeks for offline analysis to surface an anomaly. This technological revolution is especially relevant as we consider 3I Atlas's journey through the solar system. If this interstellar visitor truly bears some relation to the WOW signal, if both the components of a grand interstellar communications program, then the best time to search for repeat transmissions is as the comet passes the major bodies of the solar system. The hydrogen line offers a perfect window, precisely defined, universally recognized, and carefully protected from interference. As 3I Atlas approaches Mars, swings around the Sun and comes near Earth, radio telescopes worldwide will have a chance to listen at the exact frequency where the WOW signal first appeared 40 years ago. Whether or not we hear anything, the search itself carries profound significance. It represents humanity's sustained exploration of whether we are alone, and our willingness to listen for messages written in the universe's most fundamental language. Part 5: Why Sagittarius Matters. When ancient astronomers gazed at the constellation of Sagittarius, they saw a centaur archer drawing his bow toward the heart of the Milky Way. They could not have known they were staring at the most extraordinary district of our galaxy, a place where stars are packed so tightly and phenomena so abundant that it feels like a science fiction fever dream made real. Sagittarius holds a singular place in our night sky. Unlike most constellations which are chance alignments of distant suns, Sagittarius marks a true cosmic landmark. When we trace those familiar star patterns, we are in fact looking straight toward the Milky Way's center, the heart of its gravity and energy. 26,000 light-years away, hidden behind vast clouds of interstellar dust, lies one of the most extreme objects in the universe, Sagittarius A, a supermassive black hole about 4.3 million times the mass of our Sun. This gravitational monster helps keep the galaxy in order, gripping the orbits of tens of billions of stars while occasionally devouring any matter that wanders too close. The region around Sagittarius Mole defies easy description. Stellar density climbs to nearly unimaginable levels, far beyond that of the galaxy's quieter neighborhoods. At the galactic center, stellar density is so high that any planetary system would be constantly jostled by gravitational perturbations. Radiation levels are extreme, harsh enough to render worlds uninhabitable. Magnetic fields kink and snap, releasing energies far beyond anything in our local neighborhood. This cosmic maelstrom is both a paradise and a nightmare for radio astronomers. The center of the Milky Way pours out more radio emission than any other region of our sky. When Karl Jansky first detected radio waves from space in 1932, the strongest source he stumbled upon came from the direction of Sagittarius. Part 6: The Arrival of 3I Atlas. On July 1, 2025, while much of the world slept, an automated telescope array in Chile's Atacama Desert was methodically imaging the night sky, searching for asteroids that might threaten Earth. The Atlas survey, the Asteroid Terrestrial Impact Last Alert System, has kept this vigil for years, logging countless rocks in quiet, sun-bound orbits. But on this night the cameras caught something unusual, an object streaking across the starry background at remarkable speed, instantly tripping the detection algorithms. It clearly did not belong to our solar system. Its track mapped a hyperbolic path, meaning it was not gravitationally bound to the Sun at all, but a temporary visitor merely deflected before continuing on through interstellar space. The Discovery team, led by Atlas principal investigator John Tonry, quickly realized they had stumbled upon a historic astronomical event. Preliminary orbit solutions returned an eccentricity greater than 1, far beyond the range of typical planetary and asteroidal paths, the mathematical signature of an interstellar wanderer. This was not a main belt asteroid that had drifted off course, nor a long-period comet jarred loose from the Oort cloud. 3I/Atlas, as it came to be named, is a true visitor from beyond the Sun's domain. Within hours, observatories around the world swung their telescopes toward the mysterious interstellar visitor. Astronomers raced to collect as much data as possible before the object's trajectory carried it back out of the solar system. Unlike Oumuamua, which in 2017 was discovered after perihelion and was already speeding back into interstellar space, 3I/A was still inbound, offering months of detailed observation. Early results showed that 3I/ is unlike the objects native to our solar system. As it approached the Sun, solar radiation began to awaken volatiles in its core, raising a hazy coma of gas and dust that soon developed a distinct tail. Classic cometary behavior, but 3I/ is no ordinary comet. Spectral analysis revealed chemistry markedly different from what we're used to. Data captured by the James Webb Space Telescope indicate unusually high levels of carbon dioxide, with the ratio of CO2 to water vapor coming in at roughly 8:1. By initial measures, most comets from our system show the opposite preference, with water vapor typically dominating. As summer gave way to autumn, 3I/A continued to brighten, its activity ramped up by solar radiation. By late August, astronomers were noting vigorous cometary behavior at remarkably large distances. Most objects from the outer reaches of the solar system don't switch on until they get much closer to the Sun, but 3I/A was already lively, hinting at an unusual inventory of volatiles or an exceptional sensitivity to sunlight, yet its overall brightness remained frustratingly modest. Peak visual magnitude is projected to be only about 11 to 13, far too faint for the naked eye and requiring fairly large telescopes for detailed observation. Unlike celebrity comets such as Hale-Bopp or Hyakutake, 3I/A will be a target primarily for professional astronomers and well-equipped amateurs. As news of the discovery spread, the public's first question was about safety. NASA and other space agencies quickly computed its future path and confirmed that 3I/A poses no threat to Earth at any point in its solar passage. Its closest approach to our planet will occur on December 19, 2025, at roughly 270 million kilometers, about twice the Earth-Sun distance. The discovery carries historic weight. This is humanity's third confirmed interstellar object. The first, 1I Oumuamua 2017, left a trail of puzzles with its extreme elongation and mysterious non-gravitational acceleration. The second, 2I Borisov 2019, looked more like a conventional comet, yet still bore chemical fingerprints of formation around another star. 3I/A stands apart in one crucial way. It was found early on the inbound leg, granting us a months-long continuous observing window. That has let the full arsenal of modern astronomy go to work on a bona fide sample of matter forged in an alien system. Every spectrum, every image, every measurement enriching our picture of how planetary systems form beyond the Sun. More tantalizing still, 3I/A seems to hail from the same general direction as that famous radio signal Sagittarius. Both the WOW signal and this interstellar visitor point toward the Milky Way's bustling heart, a realm utterly unlike the suburbs of our local cosmic neighborhood. And while scientists are careful to note that Sagittarius spans a vast angle on the sky, too broad to overinterpret statistically, the coincidence is hard to ignore. So as professional facilities commence intensive monitoring and sky watchers around the world turn their telescopes toward this cosmic traveler, a single question lingers behind every observation. Is 3I/Atlas merely another natural shard forged beside a distant star, and eons later, passing by chance, or does it share a deeper tie to that radio whisper that has haunted SETI researchers for decades? The answer can only be found in the data. Part 7. Signs of the Unnatural. As observations of 3I/Atlas piled up through the summer of 2025, a picture began to emerge, one that challenged conventional expectations. Each new spectrum, each high-resolution image, each photometric measurement seemed to add another piece to a puzzle designed to confound astronomers. The most striking anomaly lies in its chemistry. Infrared data from the James Webb Space Telescope show an unusually high abundance of carbon dioxide relative to water in the coma, about 8. In our local sample of solar system comets, the trend is typically reversed, with water dominating. This chemical inversion implies a formation environment markedly different from the planetary systems we know, perhaps around a hotter, more massive star, or one with a distinct heavy element enrichment. But CO2 dominance isn't the only riddle. As 3I/Atlas moved deeper inward, it began to display what observers cautiously called overperformance. Hubble's measurements capped the nucleus at no more than about 5.6 kilometers across, with some analyses even hinting it could be only a few hundred meters. Yet this pint-size object is releasing gas and dust on par with or exceeding much larger comets. as if its interior materials are unusually volatile, or its internal architecture somehow optimizes sublimation efficiency. Spectroscopy added another layer of strangeness. Chile's Very Large Telescope, VLT, detected strong nickel atomic emission lines in the coma, common enough in many comets, but puzzlingly the iron that typically accompanies nickel was almost nowhere to be found. Given that nickel and iron share similar chemistry in cosmic environments and often cohabit the same mineral phases, this nickel without iron fingerprint left comet chemistry experts scratching their heads. Explanations sprouted quickly. Some proposed that iron may be locked in less volatile chemical phases that require higher temperatures to release, perhaps only showing itself as perihelion approaches. Others wondered whether the object's birth environment intrinsically favored nickel-rich, iron-poor mineralogy, baking in an abundant split from the start. Meanwhile, the orbital details are equally intriguing. 3I Atlas is entering the inner solar system on a retrograde path, with an inclination of only about 5 to relative to the ecliptic, geometrically close to the planetary plane, yet traveling the wrong way like a car driving against traffic. Retrograde motion isn't impossible, but it's statistically uncommon. If interstellar traffic arrived from random directions, this geometrical alignment adds one more layer to an already growing stack of coincidences. Earlier, long-range premature activity was repeatedly noted. Many visitors from the solar system's outer realms don't wake up until they are much closer to the Sun, yet 3I Atlas was already sporting a vigorous coma and tail at 3 to 4 astronomical units. That either points to an unusual volatile inventory or suggests an exceptional sensitivity to solar heating. These accumulating anomalies inevitably drew the attention of technosignature researchers. Harvey Loeb of Harvard, who previously stirred debate by proposing that Oumuamua might be alien technology, began mining the emerging data for hints of a non-natural origin. Loeb's preliminary assessment zeroed in on the object's overperformance and odd chemistry, arguing that they might qualify as technological signatures, for example CO2 dominance, not as a relic of primordial condensation, but as a byproduct of some industrial process, and the nickel without iron emission as a potential marker of engineered materials with distinctive metallurgical properties. Mainstream astronomers have responded with characteristic caution and skepticism. Jason Wright of Penn State and others emphasize that extraordinary claims require extraordinary evidence, and 3I Atlas is not there yet. On present observations, it behaves like a textbook comet, forming a coma and tail, responding predictably to solar heating, and following a purely gravitational trajectory with no sign of maneuvering that would imply technological control. Its chemical oddities may admit natural explanations. They could reflect formation around a star unlike the Sun, or arise from differences in internal structure and thermal evolution that alter how volatiles sublimate and vent. Even so, even the most cautious scholars concede that 3I Atlas's 1-2 combo is something humanity has never seen. Anomalous chemistry, a pint-sized body with outsized activity, and a stacked space-time coincidence with the WOW signal from the same general direction, all of which makes pure randomness feel off. As observations roll into the autumn of 2025, and the target closes in on Mars and the Sun, the verdict is still out. Is 3I Atlas an extreme but natural comet, or a technological artifact in disguise? The answer will depend on whether these anomalies read more like the signatures of extraterrestrial engineering, or like a margin note reminding us that our understanding of alien planetary system chemistry is still incomplete. Part 8. Back to Sagittarius. In the dot-connecting detective game of astronomy, some patterns are hard to ignore, even when reason whispers it might just be coincidence. The directional link between the WOW signal and 3I Atlas is exactly that sort of intriguing yet inconclusive alignment. Striking enough to grab our attention, not strong enough to deliver a verdict. NASA's orbital analysis confirmed the initial impression. The object's incoming radiant, its direction of arrival on the celestial sphere, lies broadly within Sagittarius, falling near the putative origin region of the 1977 WOW signal. Not a precise overlap, but enough to qualify as a positional coincidence. To judge what that means, you have to think in angles. Under the traditional constellation boundaries, Sagittarius spans roughly 30 degrees of sky, about like tiling 600 full moons into a grid. The reanalyzed WOW error ellipse is on the order of 8 arc minutes, 3 iotowns and miniaturity optic ace. Statistically, Sagittarius covers about 1/15 of the entire sky with only 2 cases. Claiming a significant correlation is essentially meaningless. But Sagittarius is hardly just any patch of sky. It faces the galaxy's most active, most densely populated core, naturally radio loud to the extreme, making it both the most conspicuous place to hunt for technosignatures and the hardest place to tease an artificial signal out of nature's din. The classic cocktail party problem. Strategically, a galactic center teeming with stars has real appeal as a broadcast hub. Observationally, the abundance of natural sources makes it the very place most likely to camouflage artificial traits. Shift the focus from bearing to dynamics and the story gets messier. Debris flung out by planetary systems near the galactic center will, over millions to billions of years, diffuse throughout the disk and eventually drift into our local neighborhood. If 3I Atlas does lie along this line of sight, it could be a fossil sample from one of the galaxy's busiest stellar factories. What really strains the coincidence argument is the timeline. The universe is 13.8 billion years old. Humans have used radio for barely 150. If the two phenomena are unrelated, their arrival within such a cosmic blink feels awfully well timed. Conversely, if the visitor were artificially guided and deliberately timed, its overlap with our "we've just learned to listen and look" era would make sense, and yet every observation so far still says it behaves like a comet. No controlled maneuvers, no structured radio emissions, no materials that demand artificial manufacture. The correlation remains. The evidence does not, yet. Maybe this is just humanity's pattern addiction. Maybe it simply reveals the galactic center's inherently busy nature. Or maybe our cosmic neighborhood is more active and interconnected than we dare imagine. To cut through the haze, we need sample size. Wide-field surveys, such as the soon-to-commence Legacy Survey of Space and Time, LSST, will likely discover hundreds to thousands of interstellar visitors this decade, telling us whether 3I Atlas is typical or an outlier. Radio observatories are also gaining sensitivity and data processing muscle. If a short burst akin to the WOW signal reappears from the direction of Sagittarius, especially coincident with 3I Atlas's passage, the pure coincidence hypothesis will be much harder to maintain. Until then, we have questions, not answers, patterns, not verdicts. Part 9. The Encounter Timeline. The celestial clockwork governing 3I Atlas's passage through the solar system has been computed with exquisite precision. Unlike the WOW signal, here one moment and gone the next, this interstellar visitor's itinerary is predictable and plannable, giving us multiple windows to zoom in and perhaps to resolve the mysteries. The first stop comes quickly. In early October 2025, 3I Atlas will skim past Mars at a closest distance of about 30 million kilometers. The European Space Agency has confirmed that several Mars orbiters, including the ExoMars Trace Gas Orbiter, TGO, and Mars Express, will attempt coordinated observations. This won't just be multi-camera imaging. Tiny perturbations to spacecraft trajectories could even be used to back out the visitor's mass and interior structure. The timing around October 2-3 coincides with the run-up to peak activity, and spectroscopy will test earlier chemical anomalies. Do the nickel lines persist? Does iron arrive late? After that, it will race toward perihelion. Calculations indicate that on October 29-30, 2025, it will pass perihelion at about 1.4 astronomical units from the Sun, inside Mars's orbit but still outside Earth's. For any cometary nucleus, that's oven time, sublimation at its peak, morphology changing fastest, and if there's anything unusual about its interior or materials, it's most likely to give itself away then. Unfortunately, Earth-based observations will be severely limited by solar limb glare. The load will fall to space telescopes with suitable stray light suppression, Hubble JWST, to grab precious time slots. Ground facilities will likely have to wait until early December, when its solar elongation widens enough for it to return to the night. On December 19, 2025, it will make its closest approach to Earth at roughly 270 million kilometers, about 2 AU. It won't be a naked-eye comet, but the geometry will be ideal for hunting possible radio transmissions, Doppler effects minimized, distance relatively small, round-the-clock monitoring feasible. If it bears a hidden kinship to the WOW signal, this is the prime hold-the-frequency window. The same interval is also best for checking for tiny sustained non-gravitational accelerations, millimeters per second, to probe for covert propulsion or controlled attitude changes. Moving into 2026, 3I Atlas will recede outward and stage its final major planet roadshow. On March 16, it will pass Jupiter at about 0.36 astronomical units, roughly 54 million kilometers. This will be its closest brush with any planet, offering a unique laboratory for studying how interstellar material interacts with a giant magnetosphere. Mission planners can't help daydreaming about a drive-by look from Juno or JUICE, but the realities of propellant and mission priorities make that exceedingly difficult. Even without a spacecraft escort, ground-based observatories can use Jupiter as a backdrop to record how the visitor's tail and coma behave in a strong magnetic environment, the last reel of film before it runs away from home. After that, it will slip farther away, its brightness fading day by day, and ultimately return to the interstellar night without looking back. This single passage is humanity's only chance to study this extrasolar sample. From the July 2025 discovery to the final glimpse in late 2026 is roughly 18 months, an unprecedentedly long window that lets us coordinate across wavelengths, track chemical evolution systematically, and conduct organized technosignature searches at the hydrogen line and other key bands. The cosmic stage is set. We must watch, we must listen, and we must dare to imagine. Part 10. A house divided. Scientifically, in an astronomical community that is usually collegial, agreeing to disagree with grace, 3i Atlas has sparked an uncommon collision of viewpoints. It has dragged deeper fault lines into the open. Faced with anomalies, how should we adjudicate them? Where exactly should the evidentiary bar be set? The mainstream consensus NASA, ESA, and most observatory teams holds that 3i Atlas is a natural comet. Odd, yes, but still within the bounds of explainable by nature. This stance stresses that it looks like a comet from head to tail. It grows a coma and tail, responds to solar heating in model-consistent ways, and its orbital dynamics are entirely gravity-driven. The chemical peculiarities, CO2 dominance, the nickel-iron asymmetry, and a small body overproducing dust and gas are more likely the products of formation in a non-solar stellar environment, or of differences in internal structure and thermal history. As small body expert Alan Fitzsimmons of Queen's University Belfast notes, we have seen only 3 interstellar visitors. Talk of typical versus atypical is hamstrung by sample size. Hubble's latest constraints, a nucleus no larger than Chandrayaan 5.6 kilometers, with some interpretations leaning smaller, down to a few hundred meters, also give a physical footing for the high output. A small body's high surface area to volume ratio naturally favors vigorous sublimation. On the other side, R.V. Loeb has continued his tradition of bold questions, emphasizing the probability gap created by the stacked coincidences and sketching a framework for a possible reconnaissance/communications mission. In response, Jason Wright and others have been blunt. Every anomaly presently admits natural explanations until hard techno-signatures appear. Controlled maneuvers, structured narrowband emissions, or materials that cannot arise from natural processes. Science should hew to Occam's razor. The debate has also spilled into the question of how science communicates with the public. Media coverage often conflates preprint/blog hypotheses with peer-reviewed results, yielding headlines that declare either alien probe confirmed or 100% natural, misleading audiences and distorting funding landscapes. In recent years, the International Astronomical Union and SETI organizations have increasingly stressed that candidate anomalies should be presented with parallel hypotheses and subjected to rigorous cross-checks before public release. Meanwhile, observations continue apace. Spectroscopy has confirmed the persistence of some anomalies while revealing new layers of complexity. Photometry has tracked changes in brightness and color, hinting at surface inhomogeneities or rotation-driven modulation, and systematic radio listening is underway, from the Very Large Array to Green Bank staking out the hydrogen line and other key windows, with radio silence so far. Skeptics take that silence as further support for the natural camp. Advocates counter that silence could mean awaiting a trigger, or communication modes beyond our current reception. As 3i Atlas closes in on Mars and the Sun, the stakes rise. The appearance of any smoking gun artificial feature would render today's argument a mere prelude. If it remains alien-born yet natural, this episode will stand as a masterclass in how we evaluate anomalies. Either way, 3i Atlas has forced us to confront both our evidentiary thresholds and the scope of our imagination. Part 11. Coincidence or contact. Human brains are wired to find patterns in clutter and meaning and randomness, a survival trait that once helped our ancestors tell signal from noise in grass and shadow. But scaled up to cosmic mysteries, that instinct can mislead us. We connect unrelated dots and mistake coincidence for causation. The supposed relationship between the WOW signal and 3i Atlas is a psychological litmus test of exactly this kind. 2 anomalies nearly half a century apart, pointing to the same general direction, too coincidental at first blush. Yet once we coolly unpack it, the linkage looks far less ironclad. The relocalized WOW error ellipse is still on the order of 8 arc minutes. 3i Atlas's radiant uncertainty is of similar scale, yet offset by several degrees on cosmic terms, a gulf of millions of light years, nowhere near a precise pointing. The timing coincidence cuts both ways as well. If the object has wandered interstellar space for millions or billions of years, the fact that it just happens to show up in the mere century when humans can listen, was that chosen, or just colossal chance? Without hard evidence of origin and age, no firm verdict is possible. That both point toward Sagittarius adds complexity, not clarity. It's the noisiest, busiest district of the Milky Way, where natural sources can easily masquerade as artificial features. And with a sample set of only one non-repeating radio anomaly, plus 3 interstellar visitors, any statistical inference is on shaky ground. We don't yet know how common such events are, or whether they cluster in space and time. Part 12. The message in motion hypothesis. This hypothesis proposes that if an advanced civilization wished to communicate, it might choose to deliver information via a physical probe rather than radio, say by masquerading as a natural comet and triggering transmissions, or revealing non-natural traits at key geometric moments, planetary flybys, perihelion, etc. To test this, we must rigorously disentangle possible natural thermal effects and rotation-driven venting from any putative artificial heat sources or device behaviors, work that demands ultra-precise measurements and sophisticated modeling. Logically, the idea faces tough questions. If the goal is communication, why not use near-instantaneous radio rather than invest vast resources and accept years to millennia of risk to launch a physical mail carrier? If contact is intended, why disguise the device as a comet and add ambiguity? Wouldn't more direct technosignatures, an unmistakably engineered shape, or an active broadcast be more effective? These objections don't falsify the hypothesis, but they highlight its extraordinary premises. Perhaps alien communication strategies follow principles we don't yet grasp. Perhaps physical probes carry capabilities or payloads that radio cannot convey. Perhaps concealment reflects caution toward potentially hostile civilizations. Either way, the strictest test window is imminent. Should 3I Atlas exhibit controlled maneuvers, structured narrowband emissions, or material properties impossible in nature, message in motion would shift from bold conjecture to revolutionary discovery. If instead, observations continue to favor a natural comet interpretation, the hypothesis will join the imaginative but incorrect shelf, while teaching us how to separate genuine anomalies from the products of human pattern seeking. The beauty of science is not in shunning bold ideas, but in testing them, honestly and rigorously. Part 13. The act of listening. Amid the ever-present cosmic radio symphony, hearing an artificial signal demands both cutting-edge technology and deep patience. As 3I Atlas threads the solar system, the global radio astronomy community is preparing what may become the most intensive coordinated SETI campaign in history, timed to the windows when geometry and distance are most favorable. The first key window is the early October Mars flyby. If this visitor were programmed to respond to planetary gravity or magnetic environments, that could be the moment of initial activation. The more dramatic window arrives at late October perihelion. As solar heating peaks, the intense radiation environment could awaken dormant systems, boot a communications array, or trigger a self-announcement aimed at any watching civilization. Part 13. The act of listening. Amid the ever-present cosmic radio symphony, hearing an artificial signal demands both cutting-edge technology and deep patience. As 3I Atlas threads the solar system, the global radio astronomy community is preparing what may become the most intensive coordinated SETI campaign in history, timed to the windows when geometry and distance are most favorable. The first key window is the early October Mars flyby. If this visitor were programmed to respond to planetary gravity or magnetic environments, that could be the moment of initial activation. The more dramatic window arrives at late October perihelion. As solar heating peaks, the intense radiation environment could awaken dormant systems, boot a communications array, or trigger a self-announcement aimed at any watching civilization. Part 14. The bigger picture prelude. The technologies and methods driven by the study of interstellar visitors pay dividends across astronomy. Improved fast-mover detection algorithms sharpen our ability to track potential near-Earth threats. Finer spectroscopic techniques deepen our understanding of comets and asteroids within the solar system. And stronger international coordination lets the global community respond more swiftly to time-sensitive discoveries. Most importantly, objects like 3I Atlas force us to confront the edges of our knowledge, while staying open to possibilities that exceed our imagination. As it advances toward pivotal encounters with the inner solar system, Mars, the Sun, and Earth, every spectrum we capture, every frame we image, every measurement we log, adds to humanity's shared understanding of the environment between the stars. Pulling back the lens, the bigger picture comes into focus. The universe is far more dynamic and interconnected than earlier generations imagined. Matter, and perhaps even life, may migrate between stars in ways we do not yet fully grasp. Each world may, in some fashion, influence another, and the next discovery could fundamentally rewrite how we see ourselves within a broader cosmic community. The technological and methodological advances driven by the study of interstellar visitors are benefiting the wider field of astronomy. Improved algorithms for detecting fast-moving targets have enhanced our ability to track potentially hazardous asteroids. Finer spectroscopic techniques have deepened our understanding of comets and asteroids within the solar system, and more robust international coordination has strengthened the global community's rapid response to time-sensitive discoveries. Perhaps more importantly, objects like 3i Atlas force us to confront the limits of what we know while keeping an open mind. Its anomalous traits remind us that the universe keeps surprising us, challenging our assumptions and revealing phenomena we have not yet learned to anticipate. As 3i presses into the inner solar system and approaches key encounters with Mars, the Sun, and Earth, it carries humanity's collective curiosity and technical capabilities with it. Every spectrum we collect, every frame we image, every measurement we make adds to our grasp of the cosmic environment we share with countless other worlds. Whether 3i ultimately proves to be an alien-born yet natural comet, or something more extraordinary, its passage through the solar system is a milestone in humanity's cosmic maturity. We are no longer distant onlookers, but active participants in a cosmic community that regularly welcomes visitors from elsewhere, each bearing stories and secrets from between the stars. The bigger picture thus comes into sharper focus. The universe is far more dynamic and interconnected than earlier generations imagined. Matter and perhaps even life may be migrating between stars in ways we do not yet fully understand. Each world may in some fashion influence another, and the next discovery could fundamentally redraw our place within this wider cosmic community. Part 15. Epilogue. Waiting for the next wow. We are no longer content to merely catalogue what we see. We have begun to seek, proactively, signs of another mind among the stars. Are we alone is among the most profound questions any species can ask. The connection between that mysterious radio signal and a perplexing interstellar visitor hasn't given us a definitive answer, but it has offered something just as valuable, a framework for thinking about how the answer might appear. In the months ahead, as 3i continues its passage through the solar system, and our instruments keep vigilant watch, we inherit the hard-won wisdom of generations who looked up and wondered, is someone over there looking back at us? Their curiosity is our legacy, their question, our mission. The next wow moment may arrive tomorrow, next year, or decades from now. It could come as a radio transmission, a flash of optical light, or a visitor from the stars revealing unmistakably artificial traits. Whenever it comes, and the optimist inside every scientist believes it will be ready. We have built the instruments, drafted the playbooks, and refined the intellectual framework needed to identify, verify, and respond to evidence of extraterrestrial intelligence. More importantly, we keep alive the sense of wonder and possibility that underwrites every great discovery. The universe is vast and ancient. The number of stars exceeds the grains of sand on Earth. Among countless suns, the laws of physics and chemistry have had billions of years to breed complexity, diversity, and perhaps forms of intelligence beyond our imagination. The juxtaposition of the WOW signal and 3i reminds us that in such a cosmos, anything is possible, and the most unusual possibilities are often the most worth pursuing. As we pause this chapter of cosmic inquiry, what we've gained is not a final answer, but better questions, not absolute certainty, but a more mature method of search, not a single conclusion, but a confidence that our species has the tools and the resolve to keep seeking truth among the stars. The universe keeps its secrets well, but we have proved ourselves persistent students. Whether we are alone in this vast space-time or not, the search itself ennobles us, challenges us, and binds us to something larger than ourselves and larger than Earth. Perhaps that is the greatest discovery, not only that we can ask these questions, but that we have the courage to follow the answers into the interstellar dark.